Welcome to C.3. In this video, we're going to see how the half-life is the time it takes for half the number of atoms to decay. Then we're going to look at the solution of radioactive decay problems involving integral or whole numbers of half-lives. And since we're talking about writing equations, we're going to stick in here deduction of nuclear equations for fission reactions. So the first thing we want to do is we want to summarize the difference and make it clear in our heads what are the differences between chemical and nuclear reactions. So you can see here that chemical reactions are due to atoms being rearranged, and nuclear reactions are due to elements actually being converted from one to another. In a chemical reaction, we have only electrons that are going to be involved, whereas nuclear reactions, we have protons, neutrons, and electrons being involved depending on the cases you'll see. For the third difference, we have reactions that are accompanied by relatively small amounts of energy, but nuclear reactions, we know, release a lot of energy. And number 4, we can sort of alter the chemical rates of reaction, sort of taking a look back at the kinetics unit by temperature, pressure, concentration, and catalyst, whereas nuclear reactions are not really affected by that. So our next step is sort of to understand why some things are radioactive and why some are not. So to do that, we're going to go to this build an atom. And what we're going to do is we're going to build a hydrogen. Let's go a little bit. Let's go to carbon, because that one's fairly common with radioactive dating. So carbon, and I'll make, first of all, carbon 12, which means that it has 6 protons and 6 neutrons. And so you can see right now everything is stable. But let's see what happens if I add another neutron and make it to carbon 14. All of a sudden it's unstable. In other words, it can be radioactive and it can actually turn into a new element over time. If I add more, it continues to be unstable. If I go back to where it was stable, carbon 13 is stable. It wouldn't undergo radioactive decay. Carbon 12 as well. Oops, grabbed the wrong one there. But look at that. As soon as I go below, now that I'm at carbon 11, it's unstable again. So what's kind of going on here? Well, we have to take a look back at the types of forces that are involved. So we have the electromagnetic force, which is essentially the protons repelling each other because they're both positive. And then we have the neutrons, which are supplying the attractive, strong nuclear force. Now the thing about this is the strong nuclear force is much stronger than the electromagnetic force over short distances, whereas over longer distances the electromagnetic force is stronger than the strong nuclear force. So what we have is there's a balance between the repulsive electromagnetic force and the attractive nuclear force. So as a nucleus becomes bigger from too many neutrons, so for example, if I add these back in, now it's going to be too big. What's happened is the fact that these protons are getting further apart, and as distance increases, the fact of the matter is that electromagnetic force becomes stronger than the nuclear force, so it becomes unstable. If there are too few neutrons, by us removing them away and we make a small nucleus again, it can become unstable again because there's not enough strong force to overcome the electromagnetic repulsion. You have too many positives getting close together, and that will cause there to be more repulsion. It's not really diluted much by the presence of other neutrons. So what we end up with is what we call a band of stability. So over here we have the number of protons that an atom may have and the number of neutrons that it may have. And in the middle here, this dot, all these dots, this sort of shows the band of stability where the proton to neutron ratio is in balance to give you a stable nucleus. But for example, if you have a high number of neutrons compared to number of protons, then you have beta emitters, and what they're going to do is they're going to actually become more stable, and you'll see how, by trying to increase the number of protons. And over here, these ones down here, they have too few neutrons to be stable. And so what they're going to actually do is they're going to emit alpha particles in an attempt to get rid of number of protons, and thus sort of increase the ratio of neutrons to protons. So in the middle there, that is where we get a stable nucleus. So what do we mean when we talk about what they're emitting? Well, there's a few things they can emit. So imagine this is a radioactive or unstable nucleus. Well, one thing they could do is they could do alpha radiation. And in alpha radiation is they emit 2 protons and 2 neutrons. And that's what we call alpha decay. Now, we often call this a helium nucleus. So by doing that, they'll get rid of 2 protons, 2 neutrons, but usually what ends up happening is you increase the number or the ratio of neutrons to protons, making the nucleus more stable. Another option is called beta radiation or beta decay. And what happens there is an electron is emitted. And when that happens, it's emitted from a neutron. And when that neutron emits a electron, it becomes positive, or it becomes a proton. So what this would do is, if you don't have if you have too many neutrons, then it can decay and become a proton. And then the last one is just an unstable nucleus that sort of just shifts around. Nothing changes in terms of their identity. The neutrons stay neutrons, the protons stay protons. Nothing is emitted. But what happens is they just shift around inside and just reorganize into a more stable arrangement. And when they do that, they send out light. And the light here is in the gamma part of the electromagnetic spectrum, so gamma rays. So here's that alpha nucleus, or that alpha decay, which is a helium nucleus. Because it's big, it's made of 4 particles, it really can't go through skin or paper. It will actually impact, and then it can actually damage those types of surfaces, but it's kind of easy to shield from. Beta decay, which is the electron, as you know, since its atoms are mostly empty space and the electron is quite small, they can usually pass through paper, but if you get to something eventually a little more dense like aluminum, it tends to be blocked or shielded by aluminum and can be absorbed. The gamma decay, which is just light energy, it's not made of a physical particle. That one is just high energy, and again, it can go through the atom because it's mostly empty space, and you need some really, really thick and dense material, for example, like lead, in order for you to shield against that. So let's summarize this and take a look at how we can actually write reactions for these. So in the case of an alpha particle, for example, if we start with uranium-238, and we write the symbol for it like this. Let me make that a little bit bigger for you. And what would happen is, since this is alpha decay, it loses 2 neutrons and 2 protons. So its overall mass decreases by 4. So we can see that transition happen there. And that 4 is accounted for by this helium over here. So when we write these types of equations, we need to make sure that the mass number is conserved and that the charge is conserved here as well. So here we have 92 protons on the left-hand side, that's uranium. After it lost 2 protons, it's a new element, thorium. So this is 90, and the other 2 protons are here. So we didn't lose any. There's still 92 protons in total, overall charge of 92, and so that's balanced. With beta decay, we have a nucleus that releases the electron, and that's essentially a neutron turning into a proton. So the remaining atom will have the same mass, because neutrons and protons are essentially the same mass, but we will have, instead of 53 as the atomic number, it's now 54 because we have 1 more proton. So iodine now becomes xenon. Then to balance out the charges, it was 53 on the left, 54 minus 1 is 53. Gamma decay is when the nucleus goes from a high energy state to a low energy state. The nucleus remains the same, like we saw, it just emits a gamma ray, which is light, it's not made of matter. So the mass numbers won't change, and the charges won't change, the atomic numbers. We just show the energy being released this way. Now, positron and electron capture, those are optional extensions that you don't necessarily need to know for the DP. Alright, so what we need to do now is sort of summarize how do we balance nuclear equations. And the first thing we need to do, there's really two rules. The first rule is conserve the mass number. So the mass number is the number written in the top left. So what you want to do is make sure whatever is on the left-hand side, which is the protons and neutrons, together add up to what's on the right-hand side. There's no magic. We can't lose or gain anything. Otherwise, we violate the law of conservation of mass. So on the left-hand side, we can see 235 plus 1 is 236. On the right-hand side, if we go 138 plus 96 plus 1, we can see we get to 135. Well, that doesn't add up. 236 and 235, we lost something. So to balance that, we have to put a 2 here so that we have 2 times 1 neutron. So this n representing a neutron. And now when we do that, everything will equal. So that's how we can balance to make sure everything works out. The sum of nuclear charges in the products must equal the sum of nuclear charges in the reactants. That's our second rule. So for that one, we look at the bottom left. So 92 protons plus 0 protons and a neutron. So we have to make sure that the right-hand side adds up to 92. So we have 55 plus 37. Oh, bam, that works. So that is conserved. And that's how we would always go about balancing nuclear equations. So now that we know that, we want to take a look at how we can actually apply this in sort of everyday life. One way we can do this is by looking at radioactive dating, which is carbon-14 dating. Now, carbon-14, like we saw when we were building earlier, is an unstable isotope. So it will actually undergo radioactive decay. It actually undergoes beta decay. And what it means is it emits an electron and turns into nitrogen-14. So it does that every 5,730 years. So a half-life is essentially how long in time it takes for half of a sample to decay. So let's say you start with 100% of carbon-14, which is when things die, they start with 100% of what they die with. And if you were to come visit that sort of remnant, the fossil, 5,730 years later, then it would only have 50% left of its original carbon-14. And if you went another 5,730 years later, it would have only 25% of the original. So this is important. What you can see here is it lost 50% over 5,730 years, but then it only lost 25% over the next 5,730 years. And that's because it's all due to probability. It's kind of like flipping a coin. Every unstable isotope flips a coin essentially every 5,730 years. So when you flip a coin, if you flip 100 coins, you should end up with about 50 being heads and 50 being tails. So what would happen here is 50 of them would have decayed, so 50% decayed and became nitrogen, but 50% stayed as carbon-14. Now you are starting with only 50 coins left over that have not decayed yet. So over the next 5,730 years, you're going to sort of roll that or flip that coin again. So this time you're only flipping 50 coins, so when you get over that time period, that half-life, you're only going to have half of that left. That's 25 this time. And then if you do another half-life, you're only going to be flipping 25 coins. So you'll get about 12 and a half coins. So it keeps going like this. You keep halving it every half-life. It's half of what was left from the previous step. And you can do this with mass. So this could be 100 grams. Then you'd have 50 grams left after the first half-life, 25 after the third, 12.5 after the fourth. Or it could be concentration. You had 100 moles per liter, and then 50, and then 25, and then 12.5. So it doesn't really matter what measurement you're using as long as you have the understanding that it's halving. So the nice thing is we can actually make a graph of this. We can make a graph of the years and the percent that was left. So at 0 we started with 100. After 5,730 years, we had 50% left. After the next, which was 11,000 something, then we had 25% left. So we actually can create from that chart a curve. And this curve will allow us to solve problems graphically. So sometimes we can just make a chart and figure it out, okay, and say like, okay, after 3 half-lives, how much would be left? Well, you could just make a chart. 1 half-life is 50, 2 half-lives is 25, 3 half-lives is 12.5, 4 half-lives is 6.25. So you can figure it out that way. But if they give you something else and they're saying, okay, well, what percentage would be left after, say, 30,000 years? Well, the nice thing is once you create this graph, what you can do is you can then go to 30,000 years and then you can interpolate the answer by going over here and sort of estimating that would probably be about 3 or 4%. They could go the other way. They could ask you how many years would it be until there's only 80% left of the original carbon. So then you can go here to 80 and then you can interpolate down and try and do an estimate there and probably maybe estimate maybe 2,000 years, something like that. So there's two ways through sort of making a chart and then making a graph that you can interpret. So every radioisotope has its own characteristic decay rate. So carbon-14's is every 5,730 years, but every radioisotope will have its own half-life. But no matter what the half-life is, it's still going to be half every time. So for example, if we had something that had a half-life of, for example, 7 days, because for example some medical tracers have like iodine-131 about 7-8 days, so 1 week, what we could do is we would start with 100% of iodine 131, and then after 7 days we'd have only 50% of it left. After 14 days we'd have 25% of it left. So that's the kind of idea that we're getting at, is that it doesn't matter what isotope it is, you just get the half-life and then you do this same application of the concept.